Hello there, welcome to ECE 222 Lab. Today we have the lab introduction, so let's get started with this. So here's the lab sequence. We have Lab 0 today. This is what I'm going to present after we complete this part. So Lab 0 is going to be the introductory lab. I'm going to show you how to use Proteus, how to use Microvision to create projects, and how to simulate and debug programs with Proteus. Now for Lab 1, we have Blinky. Blinky is the implementation of a very simple application. It is just the equivalent of the Hello World for embedded systems, where we've just turn on and off an LED at a known frequency. In our case, we choose 1 Hz. Then for Lab 2, you're going to bring all the code you wrote for Blinky and extend it. You're going to use subroutines to implement the LED heliograph, which is nothing else but the same LED that you turn on and off, but with a particular pattern, so you can transmit a string in Morse code format. Now for Lab 3, we're going to implement a different application, but nonetheless we're going to be reusing code from the previous 2 labs. So the reflex meter is just a program that has the LED. Again, in this case it's going to be an RGB LED. It will turn red at the beginning for a random amount of time, then it will turn green. When it turns green, the user of the application will have to press a push button as quick as it can, and when that happens, you're going to detect that push button is being pressed and measure the time it took from the change of LED color until the button was pressed, and then that's going to be the response time that you're going to print out in the LCD in the 7-segment display. Now Lab 4 is an extension of Lab 3, where we bring interrupts for the user response and timers to have a much accurate measurement of time. So that's all the basic description for the labs. Now let's go into lab organization. So each lab is released as a package, and all the work in your case, because you're online, will be done using Proteus through remote access. Information on how to do this I'm going to present after this lab, but it's on Learn already. So package files, we have the Proteus simulation project and the code template. For Lab 0 and Lab 1 already on Learn, so you can download those 2 files and start working in your first 2 labs. I'm going to walk you through the Proteus simulation project and the code template for Lab 0 and also for Lab 1, where I'm going to explain in a future video how to approach Lab 1. So marking process and feedback. Here we are going to have submissions, so you're going to have to submit your code. In the case of Lab 1, which is the first project with lab with submissions, you're going to have to submit two solutions, one for the case A and one for the case B. You will be given a fail pass mark as stated in the syllabus after we've of course reviewed your software. There's no need to demo your programs. Of course, checklists will be released at least one week before the submission deadline, so you can check that your work meets the requirements we are putting on it. If you are able to tick most of the items in your checklist, then you know you are going to pass the labs, which is a good thing. You will know before ourselves that you already passed the labs. Now, help and support. We are providing support basically through Learn forums. So you have to go to Learn, and on Learn find the forums, and you can ask questions. I will answer them. If you need some special support, then you can also send me an email, but I would prefer you to contact me when there is no other way in which I can help you through the Learn forum. And the reason for that is because when you post a question on Learn, it's public, and my answer is going to be public too, and everybody can benefit from that. One warning here is that do not share code on Learn. Okay, so your question cannot have part of your implementation. But you can ask questions about some specific instructions. Maybe you can ask a question about a couple of instructions that are together, but nothing that can be used to help other students solve their problem. Okay, so that's it for lab organization and lab presentation for Lab0. Let's go into how to use Proteus, how to set up a project in Microvision. So when you go to learn, and let me show you first of all, learn, you go to learn to the course. You have the course here, and you go to the content page, labs. You have this big announcement here that says remote desktop access and Proteus credentials. So here you have all the information that you need to be able to access a lab computer on our department. You have so far these are the rooms that are available for you to use. This is a view of NLab. Once you connect to that, you pick ECE, and in ECE you choose one of the rooms that are in that list. For example, if I wanted to use a room in ECE public, I will pick this one. When you click here, a file, configuration file is going to be downloaded, a script that you use to connect. If you are a Mac user, you need to or a Linux user, you need to install an application that will allow you to connect. For Mac, you have to Google it. For Linux, I would recommend Remina. Then you need to use your Nexus, your user ID and password to connect to the remote computer. And after you are logged in the computer, you can open Proteus, and Proteus will likely ask you to provide also login credentials. These are the login credentials. You have the UniWaterloo as the username, and this is the password that you are going to use. Okay, read this carefully because there are other instructions that you should follow to have a successful experience using Proteus. Now, please, this is a request, log off your PC if you're not using it. I mean, when you finish, please do that so NLab can reclaim the computer and make it available for the users. And above everything, do not kick logged users out of a logged PC. And the reason for that is when you try to log in onto a computer that is being used by other users, a message is going to appear asking you whether you want to still get this person logged out of the workstation. If you say yes, then another message is going to show up on the user that is working on the computer, but that person has just 20 seconds to respond to that. So if the student went to the washroom, is looking on a book for something that a reference or something like that, is not paying attention to the screen, is going to be kicked out, and that's not good. Many times what happens is people lose hours of work, and that's not nice. If we find you are a recurrent offender onto this, then we're going to take some disciplinary measure. So that's everything that you need to know to get access to Proteus and how to connect. Here below that big announcement, we have the lab manual, and we're going to be posting the different support packages for the different labs. Right now you have Lab0 and Lab1. You should download these files and work with them on your local computer. Then we have some instructional videos. I'm going to be posting more of this as the course progresses, and we have these two reference documents for now. These two reference documents, one is the ARM thumb instruction summary. If you click here, this is just a PDF document that contains the mnemonic for the instruction and a brief description of what it does. Okay, but this is not the real reference. This is just a quick lookup table for when you don't know what the mnemonic of a particular instruction is. Well, you come here and you see, okay, this is the basic function, this is the mnemonic. Now let's move back. Let's move back if you want to consult or know what a particular instruction does and how it's structured and such, you come to this kill reference, and here on the left you have all the instructions. If, for example, you want to know what the branch instruction does, you come to B. This is the branch instruction. Here's the syntax or structure. So it has a conditional and a label, and here's the description and so on. So this is the useful information for the first time you use an instruction, or when you don't know for sure how to use it, or you have to come to this reference for more information. Okay, we're going to visit this in particular for Lab 1. Okay, so now let's get started with the part for Proteus. So I already downloaded the demo, the support package, and I put mine in C documents for this path here. So if you look at this path, it doesn't have any spaces. So make sure you use a path without spaces. You must also ensure that you're working on the C drive for that computer, that you're logged in, because if you try to use the N drive, Proteus and the compiler of Microvision, they're going to complain and they're not going to work out well. So make sure you work on the C drive. Once you finish working and before you close your session, please make sure you have a backup copy of these files. And the reason why that is so important is because next time you may, first of all, you may not be able to log in onto the same computer. Second issue is that user profiles that are left on the PCs are cleaned up regularly, and you don't know when this is going to happen. So you're in danger of losing your files if for some reason IT runs that cleanup script. Okay, it's not going to happen while you're working, but it's going to definitely happen if you're not logged in onto the computer. So you have to make a backup on the N drive or the OneDrive or whatever storage you prefer to use. Once you come back, then you have to bring that copy, work, and then save it back again. So another important thing to keep in mind is that you cannot work inside the zip folder. So if you double click here, I see this is behaving similar to a directory, but this is not the directory. I'm inside the zip file. So if I try to open these files, some of them may open, but the problem is that they're not going to work well with Proteus nor Kill Microvision. So you have to extract everything from here. So I'm going to extract the files. I don't like the way Windows does this, and I'm going to put my files here. So there we go. Let me delete this backup file. So in general, each package is going to contain the Proteus project, a lab template. This number 0, 1, 2, 3, 4 is going to change for each lab, and you have the support file, the startup STM32 F41XE. So we distribute this with every file, with every package. Now, from this point, you have to create a Microvision project. So let's go and do that. Microvision is going to show up in your menu, in your main menu for Windows. So you have to look for Kill Microvision 5. Here you have this green icon. In some computers we have Kill Microvision 5 and Microvision 4. Microvision 4 is a blue icon. Don't use that one. You need to use Microvision 5 because it's the one that has installed the support for the microcontroller we're using here. Microvision 4 does not have support for that. So you open Microvision 5. Okay, there we go. It's been opened now. Let me close this project, and we need to create a new project. So to create a new project, you just need to come to the project menu, new Microvision project, and find that folder where your project is located. So I'm going to come to demo, Lab0, and I'm going to name my project L0. Once I do that, this dialog opens up, and what we need to do here is to type the name of the microcontroller. So we're going to use the STM32F41RE, and it's important that you pick the right microcontroller. If we go back, the STM32F4 series has so many microcontrollers, right? And if you open some of these, there are even more inside them, and some have even more than one chip, like this one. It has 2 different chips. So that's why it's so important that you pick the right one. And the reason why is because the configuration file that you see here, the startup file, will configure the pinouts and many other peripheral elements just for the microcontroller you're using. So you can't use the wrong one, okay? So ours is 401 RE. And I'm going to show you where you can find this without having to come back to the video, okay? So you pick the microcontroller, click OK. Now this window shows up. Here is where you would pick what support you want if you were working on a C project. We're not, therefore we leave it like that. We click OK, and now we have an empty project. So this is our empty project. No files are associated to this because the wizard did not create any files for us. And what we need to do now is add more files to this. So add existing files to group source 1, and what happens is this window, this dialog, is going to open on the folder where we have created the project. Make sure you have either ISM, so assembly programs, or all files selected here, and that you choose these 2, Lab0 TS and Startup. When you're clicking, they are already selected. When you click on Add, the dialog is not going to close automatically, but you see that there was a change here in source group 1 where you can see the plus button showing me that there are files inside this folder. So when we open this, we see Lab0 TS and Startup STM32 F41 opens. Okay. Now for these 2 files, I'm going to first of all explain what is inside the startup file. You don't have to modify this file at all. Let me zoom. So this file you should not modify it, but you should be familiar with it, and I'm going to explain to you why. So the first thing you see here is the declarations. So to create the stack and to create the heap, and then after that you have this table here. This is what it's known as a vector table. It contains the vectors and declares what is the subroutine that is going to serve this interrupt source, and so on. So we're going to see this in more detail for Lab 4, but for now keep in mind you have this table here. Now then after that you have the main entry point. So this is how we declare a main function, and then we have the interrupt handlers. So an interrupt handler is just a subroutine that is executed when an interrupt comes into the CPU through the vectored interrupt controller. And so what happens is that the CPU is a machine that just runs instructions sequentially. So runs one instruction, then the other, until it finds an instruction that tells it to jump to another location. An interrupt is a mechanism, is a signal that gets into the CPU and tells the CPU that it must branch to one of these handlers. And the CPU will launch a specific process for that. Needs to save the context, which is just the PC of the instruction that should be executing next when you return from the ISR, and maybe some registers that it saves automatically. And after that it loads on the program counter the instruction of the handler that is going to be executed, and that's how you enter in here. Now why is this important at this time in the course? Well, when you break something in your program, when you write programs that produce a specific kind of interrupt, we call exceptions. Those exceptions are also treated similarly to interrupts. So, for example, division by zero is one example. When you have a non-valid instruction coming into the CPU, the instruction can't execute a non-valid instruction. Or when you try to access a memory location that is reserved or not valid, that will also trigger an exception. The most usual exception you find yourself is the hard fault handler. And as you can see here, the hard fault is just a branch to itself. So when you get trapped here, nothing is going to happen, but your computer is in a safe state. So what you have to do when you find yourself in this handler or any other handler, exception handler, is that you have to go back, put some breakpoints, and try to find what sequence of instructions is causing this to happen and fix the bug. That's pretty much what you have to do. Now let's move on to the lab template code. So we're going to give you a file similar to this for each lab. And so what it contains is a template. So here you see the main function implementation. So this is the header of the function. Here is where it ends. And what we have in this sequence of instruction is a program that does not do anything really interesting. It just moves values from to some registers, then assign different values between registers using the other format for the move instruction. In this case we have move with an immediate. In this case we have move with register to register, and then it adds some values and so on. So this is what we have here. It's not a very interesting program, but will allow us to go with the basics on how to debug this on Proteus. Now what you have to do once you have the project created is you have to select the target one, and you have to come to project and open the options. Sometimes this dialog will show up. That means you have selected the wrong item here on the project tree. So what we do, we close that, we pick project Lab0 project, and then we see options for target one. Okay, we open the target one options, and we click here on the output tab, and we leave the name of the project that you put there, but we add the .elf file extension. So when the linker creates our executable, it will use L0.elf and put .lef extension there that is required by Proteus. So we click OK, and now we're ready to build this project. Building uses these three buttons here. I prefer to use this one that rebuilds everything. So we build the project. If everything goes okay, you're going to have 0 errors and probably 0 warnings. You can have warnings, but you should never have errors. Now we have an image for this project. If we move back to our project folder, now you see that Microvision have created these 3 directories, and inside the objects directory we have that L0.elf file that we need for simulation with Proteus. So let's go back. Now I'm going to open Proteus. Just wait a second. Okay. Here we are with Proteus. So when you open the project file for Lab0, and it's going to be the same for Lab1 and Lab2, what we have here is the STM32 microcontroller that we're using for the course. You have the LED, and you have the push button that we're going to use. So this element is clickable, this element is active, it will turn green when we polarize this the right way. Now, after you have the project open, the first thing you need to do is to load the program here. So you double click and it opens the edit component dialog. And what you need to do now is select the program file. So we click open and go into the objects folder and pick lab0.elf. Now we have the lab0 file. So click OK and we're ready to simulate. You can start the simulation two different ways. If we start with play, the simulation will just start and now it's simulating. And it seems like nothing has happened, but if I click here in the pause button, you will see that the program stopped here on this loop. So what is going on is that basically we are staying on the same instruction. So it's executing the instruction, but this instruction is branching to itself. So to show you that, I'm going to disassemble. So to disassemble, you right click, disassembly, right click, disassembly, and you can see the actual code that was generated for these instructions. It is going to be usually a one-to-one match, but for example, in this case, for the loop B dot, we have this new comment that tells us what is the target address. Here, the target address is not clear, is implicit on the dot, but here we can see the actual address. And as you can see, the PC is going to be loaded with this value, which is exactly the same as the instruction. So this instruction is just executing itself and branching to itself all the time. There's no way to get out of this. Now, I don't like much this view, like I mentioned in my introductory video to debugging with Pro Tools. So we can close this one, simulation will stop, and then we can start with advanced simulation. So now when you do that, you're going to have floating windows. For the first project, my recommendation is that you open the source code window. I'm gonna close it so I can show you how to open it back. You can go to the debug menu, CM4, source code, and you will open up again the source code. If this disappears, that's the way you open it back. And I'm going to also open the registers for the CPU. So here we have the registers. The registers are very important because in assembly we usually deal with how registers change over time as we progress through the program. And another important group of signals here are in the APSR register. So we have the flags here. So these are the flags. We have the C for the carry, N for the negative, then we have Q and B, which we seldom use. I don't even know what they are right now, so we have to look at on the reference, and the Z flag. So we use the Z, the N, and the C most of the time. No, there were two, particularly not in this course. Okay, so the flags are very important because when you perform logic or arithmetic operations, you can modify the flags, and the values that the flags takes after such logic or arithmetic operations are used by the branch instruction to conditionally branch to different locations in your program, and that's what allows you to create control structures such as if or loops or many others. Okay, so keep that in mind, that this is very important for you. We also have the PC, the program counter, which usually points to the instruction that is being executed or where you're stopped. And we have different registers. We have from R0 to R12. Those are general purpose registers, CPU registers that you can use to write your programs. And we have the link register. It's a special kind of register from the CPU. You can read and write onto this one and some others. But for now, this is what you should be aware of. Okay, so let's go and put a breakpoint here in the first instruction, and I'm going to run this. You have these buttons here, and I prefer to use the hotkeys, which you can find here in the debug menu. So run the simulation is F12, and step over source line is F10. These two are the most frequently used. particularly in this course. So now we are stopped here at the move R0, comma number 0x5678, and what this does is it writes that value into the lower part of R0. So if I execute that instruction, we have here 5678, and move T does the same thing but writes onto the top part of the register. So if I execute this one, it writes 1 2 3 4 on the top part of R0. The reason why they work that way is because how immediates are codified within the instruction. So an immediate is just a constant value you can codify within the instruction. So when the instruction is fetched from program memory and brought into the CPU and decoded, those bits that are not used for example, the opcode, the destination register, the conditionals, and so on, can be used to store constant information. And that's why we need a move and move T to be able to load a 32 bits register, because we don't have 32 bits to store the value. So the only way you can load a full register is by writing in both the low and the high word. Okay, so now we can keep moving through the program. So as you can see, nothing really interesting happened. So R1 was written with 0 and so on. So as we move, the program will progress until, like I mentioned before, it will reach a point where it finds an instruction that branches somewhere, and in this case it's just branching to itself. So the program cannot keep moving forward from this point. That's everything I wanted to say about how to do debugging with Proteus. We're going to see a little bit more with Lab 1 in the next video. Thank you for watching, and I hope this is useful to you. Bye for now.